Hello, my name is Ty Roberts, and my senior project is a 3D procedural maze generator and solver. I've broken the project down into several pieces, starting with an intro to what exactly it is, then going into more detail about the generator itself, the solver, problems I ran into along the way, then wrapping up with what I would do differently if I were to do this project again, and then a quick recap before a demo. This project is a procedural maze generator, creating an array of integers, then turning that into a three-dimensional mesh, and placing a simulated robot into the maze to solve it. This project was inspired by the Micromouse competitions, where contestants are required to build small robots that compete to solve a maze in the shortest time possible. Then extrapolated into 3 dimensions due to a funny misunderstanding in the project proposal. The project is related to computer science because it revolves around the optimization of algorithms and it tackles the problem of pathfinding. The current generator that produces the mazes is the product of many iterations. The original generator would flip a coin for each cell in the maze and either pick open or wall, with no logic for connecting any of the cells together. Although this produced some interesting mazes with multiple solutions as well as loops, it had the problems of creating mazes with no solutions at all. The iteration that's used currently uses Prim's algorithm. Prim's algorithm is a minimum spanning tree algorithm for undirected graphs that was developed in 1930 and rediscovered and republished by Robert C. Prim. It generates a quote-unquote perfect maze, meaning there's only one solution to the maze, one path that goes from start to finish, which solves the problem of ensuring there's at least one solution to the maze that the random iteration had. Multiple floors are achieved by continuing on with the current seed of the random generator and generating another maze via Prim's algorithm, then linking the two floors at opposing corners to create the longest path possible that goes from start to finish. The solver has also had many iterations, similar to the generator. The original iteration would pick a random direction at any time it reached an intersection, and this proved to be quite inefficient though. Simple decision making such as left hand on the wall was then introduced, but this was still defeated by loops in the maze. A third iteration gave a bias of left or right, depending on whichever put the solver closer to the goal, but this also resulted in getting stuck in dead ends, with no incentives to turn around. The final iteration uses a modified A-star pathfinding algorithm using Manhattan distance, or the distance between 2 points measured along axes at right angles, to calculate a cost for each visible node, and keeps track of each node parent node, the distance to the start, and the distance to the end of the maze. This distance is then used as a cost to sort the list of nodes to explore the most promising ones first. The algorithm has been modified to remove the omnipresence, requiring the solver to backtrack over previously explored nodes so that it can get to the next promising node, instead of just teleporting to it. There was a multitude of problems with the maze generator throughout the several iterations. The first problem I encountered was the horrible disfigurement when creating mazes over 100 by 100 in size, as seen by the picture in the bottom left. This is caused by an index of 16 bits for the vertices of the mesh, but requiring over 16 bits for the size, resulting in overwriting the beginning of the maze with data from the end of the maze. This was increased by increasing the buffer to 32 bits, to which I have not reached the limit of in size, even with 2000 by 2000. The next big issue came from generating the mesh after making some changes to optimize for the generation. The mesh was being created mirrored from the grid of nodes, as seen by the red and green squares in the blue maze, where red should be the blue wall and green a black open space. The final issue that I ran into was terrible performance when generating large mazes. This was a matter of making a bunch of changes to the algorithm, moving to coroutines instead of functions, so that they're not required to run the entirety of the function before the next frame was drawn to the screen. Though at extreme sizes over 1000 by 1000 square, further optimization could still be needed and used. There were, of course, also many problems that plagued the solver. One such problem was pathing issues, where the clear path would have been to turn right, but it would turn left, go up, and then turn right. This particular problem was attributed to the cost function I was using at the time, and was phased out and solved by using the A-star solver. A similar case happened with the solver getting stuck. Code that would prevent the solver from getting stuck in loops would come back to haunt me hours later in dead ends. This again was solved with the A-star implementation. The A-star implementation also had its problems, however, as the original backtracking code I wrote was horrendous performance-wise, and also wouldn't work for all cases where the solver would need to find a path between two nodes, resulting in going all the way back to the beginning of the maze and then just going through walls and floors until it reached where it wanted to be. The A-star implementation also took a real long time to solve mazes, taking over half an hour to solve a 151 by 151 size maze. This came down to how the promising nodes were explored, where it would go to the most promising node each time. But this resulted in a lot of time spent traveling across the maze from one node to the other, and it was solved by exploring promising nodes that were nearby the solver first, cutting the time it took to move from one to the other. The final issues in this solver stemmed from the physics-based system of determining if cells were open or closed, producing a lot of overhead that dragged the frame rate down for no reason other than it seemed more accurate to actually simulate a robot with sensors. But reading values from the array that the maze was storing sped things up and made it run much smoother. If I were to do this project again, there were several improvements that I would make upon my current design. Breaking the maze down into chunks would allow for generating chunks in parallel. So instead of a 32 by 32, you could have 4 16 by 16s. And compute them all in parallel, which would speed up creating the maze. Breaking the maze into chunks would also allow for applying LOD, or level of detail, to the actual mesh of the chunk, or even hiding chunks that are out of view of the camera, to increase performance on extremely large mazes. Parallelizing Prim's algorithm may also be beneficial to reduce the time taken to generate the maze, though some research suggests that this might not be quite the performance increase. So other algorithms for generating a perfect maze might be beneficial here as well. Finally, reducing the overall memory usage by the program would go a long way for running it on lower power machines, as currently large mazes, such as a 2000 by 2000, take a significant amount of memory to run for the actual maze itself and all of the memory required for the solver. This could be accomplished by reducing some of the arrays that store duplicate data and as removing the Unity engine from the equation and using something like OpenGL directly. Alright, that was a lot of information pretty quick, so a quick recap. I've got a maze generator that uses Prim's algorithm to generate perfect mazes. These mazes are then solved by a solver using a modified version of A-star pathfinding. The generator and solver took many iterations to get to where they are now, and there are a number of changes that I would make if I were going to do this project again to increase performance for large size mazes, so I can go even higher with ridiculously sized mazes without any compromises on performance. And here's a quick demo of the project before we wrap up.